Hello everyone. So this is a question from JEE Mains 2026 6th April Shift 2. An optically active alkyl bromide C4H9Br reacts with ethanolic KOH to form A, which reacts with bromine to give B, which reacts with ethanolic KOH and sodamide to give C. One molecule of water adds to C on warming with mercuric sulfate and dilute sulfuric acid at 333 Kelvin to form D. The functional group in compound D will be confirmed by. Okay, so we have four tests given to us. The chapters involved is haloalkanes and haloarenes, hydrocarbons, aldehydes, ketones and carboxylic acids, and alcohols, phenols and ethers. Okay, so we are starting with an optically active alkyl bromide C4H9Br. Okay, a simple test of molecular chirality is the presence of a single asymmetric or chiral carbon atom in the molecule. Very important. A simple test of molecular chirality is the presence of a single asymmetric or a single chiral carbon atom in the molecule. Okay, so therefore the structure of optically active C4H9Br, that is this guy, will be, so it will look something like this: C, CH3, C2H5, H and Br. Okay, so the single asymmetric or the chiral carbon atom in the molecule is this guy. You can see it is attached to four different groups: CH3, C2H5, H and Br. Okay, the solid wedge represents above the plane of the screen. The dashed wedge represents below the plane of screen. Okay, or in simple terms I can draw this guy as CH3, CH, Br, CH2, CH3. Okay, then this guy reacts with ethanolic KOH to form major compound A. Ethanolic KOH to form major. Okay, so we should know that when a haloalkane, that is this guy in general, is a haloalkane, is heated with a concentrated alcoholic solution of potassium hydroxide, a molecule of hydrogen halide, that is HX, is eliminated and an alkene is formed. Very important. So in general, when we have haloalkane plus concentrated alcoholic solution of KOH and obviously heat, so HX plus, we get HX plus an alkene. Okay, and from this haloalkene, hydrogen is eliminated from a beta carbon, and halogen is eliminated from alpha carbon. Okay, so in our starting compound, that is this guy CH, CH3Br, CH2, CH3, we have two different beta hydrogens. That is, these are one kind of beta hydrogens. So let's say these are beta 1, and these are another kind of beta hydrogens. Let's say this is beta 2. Okay, and this is our alpha carbon. Okay, so since this guy has two different kinds of beta hydrogens, therefore two products are possible when we react this guy with uh, ethanolic KOH. Okay, so the first case is when beta 1 hydrogen goes out. So any one hydrogen from here goes out, and obviously bromine goes out from the alpha carbon. So in that case, we will get this alkene CH2 double bond, CH single bond, CH2, CH3. Okay. And the other possibility is when we remove hydrogen from beta 2, or you can say beta 2 hydrogen goes out. So any one of the hydrogen from here goes out, and obviously the bromine from alpha carbon goes out. Okay. In that case, I will get CH3, CH double bond, CH, CH3. Okay. So out of these two, this is more stable. Okay. Because according to Zaitsev's rule, more highly substituted alkene is the major product. Okay. So according to Zaitsev's rule, more highly substituted alkene are the major product. Okay. So by more highly substituted alkene, I mean alkene having lesser number of hydrogen atoms on doubly bonded carbon atoms. Okay. So here you can see on the doubly bonded carbon atoms, we have two hydrogens. On this product, on the doubly bonded carbon atoms, we have 2 plus 1, 3 hydrogen. So this is more substituted, or you can say more highly substituted. So therefore, this is the major product. Therefore, but2-ene, that is this guy, is A. So this is our A. Okay. Now next, A reacts with bromine to give B. Okay. So we should know that halogens like Cl2 or Br2 readily add to alkenes to form vicinal dihaloalkanes. Very important. Okay. Halogens like Cl2 or Br2 readily add to alkenes to form vicinal dihaloalkanes. Okay, that is, with respect to reaction, I can write A, which is CH3 CH double bond CH CH3 plus Br2. So one Br gets attached here, the other Br gets attached here, and the double bond is converted to a single bond. So therefore, I will get CH3 CH Br CH Br CH3. Okay, so this is our B. Cool. Then B reacts with ethanolic KOH and sodamide, which is NaNH2, to give C. Okay, so we should know that vicinal dihaloalkanes, that is these guys, undergo dehydrohalogenation, which is loss of hydrogen and halogen, to give alkynes when heated with an alcoholic solution of potassium hydroxide or sodamide. Okay, so vicinal dihaloalkanes undergo dehydrohalogenation, that is loss of H and X to give alkynes when heated with alcoholic solution of KOH or sodamide NaNH2. Okay, so therefore with respect to reaction, I can write, so I have B, which is CH3 CH Br CH3. So this guy is reacting with ethanolic KOH and sodamide. Okay, so therefore first, dehydrohalogenation, hydrogen from here and Bromine from here goes out, giving us a double bond. Then in the next step, hydrogen from here and halogen from here goes out to give us the triple bond. So therefore, ultimately, the product will be CH3 C triple bond C CH3. So this is our C. Okay. Then C adds a molecule of water when warmed with mercuric sulfate, which is HgSO4, and dilute sulfuric acid at 333 Kelvin to form D. Okay. So under these conditions, we should know that alkynes will add a molecule of water to the triple bond according to Markovnikov's rule to first form an enol, which tautomerizes to the corresponding carbonyl compound. Okay, important. So under these conditions of HgSO4 and sulfuric acid at 333 Kelvin, alkynes add a molecule of water to the triple bond according to Markovnikov's rule to first form an enol, which tautomerizes to the corresponding carbonyl compound. So that is with respect to reactions, I can write CH3 C triple bond C, CH3, that is our compound C, plus molecule of water HNOH, this part partial negative, this part partial positive, okay, and in the presence of HgSO4 and H2SO4. Okay, so you can see this is a symmetrical alkyne. So you can add H to this carbon or OH to this carbon, or you can add H to this carbon or OH to this carbon. Okay, if it was not symmetrical, then you should follow Markovnikov's rule. Okay, so therefore, after addition of, let's say, using arrows, I add H here and I add OH here. So therefore, I will get CH3C OH double bond CH CH3. Okay, so this is our enol. Okay, because look at this carbon has both double bond, which is ene, and also it is connected to an OH alcohol plus ol, therefore it is known as a enol. Okay, and enols can show tautomerism, and to be specific, keto enol tautomerism. Okay, enols can show keto-enol tautomerism. Okay, where the hydrogen migrates from one polyvalent atom to the third polyvalent atom within the same molecule. That is, with respect to diagram, so this is our enol form CH3COH double bond CH3. Okay, so hydrogen from a polyvalent atom migrates to the third polyvalent atom 1, 2, 3. So it migrates here, and this pi bond migrates here. Okay, so therefore this is the enol form. The keto form will be CH3 C double bond O CH2 CH3. So this is the keto form. Okay, so for more details regarding keto-enol tautomerism, you can refer to the link in the description. Okay, so this guy is our D. Okay, and D is a methyl ketone, very important. So this guy is a methyl ketone. Okay, and methyl ketones are a class of organic compound having a carbonyl group. You can see this is the carbonyl group directly attached to at least one methyl group and another carbon group. Okay, so therefore D is a methyl ketone. Okay. In option A, we have haloform test. Okay. In haloform test, we treat methyl ketones with excess of halogen in the presence of alkali to produce a haloform. Okay. We get a haloform. Now, if the halogen used is I2, then we get yellow precipitate of iodoform. Okay. And that is used as a way to identify methyl ketones. Okay. So therefore, option A is the correct answer. Coming to option B, we have Lucas test. Lucas test is used to differentiate primary, secondary, and tertiary alcohol. So therefore, this is not correct. Option C, we have silver mirror test. Silver mirror test is used to identify aldehydes, both aliphatic and aromatic. So therefore, this is not the correct answer. Option D, we have Benedict test. Benedict test is used to detect the presence of reducing sugars like glucose, fructose, maltose. Okay. So therefore, this is also not the correct answer. So therefore, the final answer is option A, that is haloform test. Okay. Thank you.